Let me now introduce today's speakers. Dan D'Aquila has a bachelor's degree in electrical engineering from Northeastern University. He has started in the motion control field in 1987 as an applications engineer with Pacific Scientific, later Danaher Motion. He went on to positions as field application engineer, field sales engineer, regional sales manager, application engineering manager, product marketing specialist, and program manager. He joined Infranor in 2007 and is currently the general manager. Robert Comstock has a bachelor's and master's degree in electrical engineering from MIT. Prior to entering the motion control field, he worked in the aerospace industry at General Dynamics, Raytheon, and the MIT Instrumentation Lab, later Draper Labs. Bob left Draper in 1980 to become engineering manager of IMEC Corporation to design drive electronics for brushless permanent magnet and induction motors. In addition to electronics design, Bob managed application support and worked with many customers to select motion control solutions for myriad applications. Currently, Bob is a consultant working with Infranor. Jack Curl holds a Bachelor of Science degree in electrical engineering from Worcester Polytechnic Institute. In 1990, Jack entered the motion control industry as an applications engineer for CMC Torque Systems. He moved on to Pacific Scientific in 1994 and later became Applications Engineering Manager. Jack went on to work at Almo Motion Control in 2006 as a field automation engineer. In 2007, Jack came to Infranor and is currently a senior systems engineer. Now let me turn things over to our presenters. Dan, the floor is yours.
Thank you, Elizabeth, and welcome everyone to Servo Sizing and Selection. In today's webinar, we're going to try to demonstrate some pretty critical sizing topics, and we're going to use an application, a two-axis robot application, to illustrate those topics. The first axis we're going to look at is the traction drive axis. And that axis is going to convert rotary to linear motion, so that's the first topic we're going to cover. And we're going to select a gear reducer. When we do that, we'll take some time to discuss why we chose the gear ratio we chose and evaluate that a little bit more. The second axis is a rotary linear axis also. It's a lift axis for for lifting the load. And so in that axis, we're using a ball screw to convert the rotary to linear motion. Of course, we're lifting against gravity, so we're going to evaluate the effects of gravity. We're also going to talk a little bit about inertia matching and why that's important when we're sizing servo applications. We're not going to spend time talking about servo performance necessarily, but just understanding why inertia matching is important. Of course, as in level 1 sizing, we're going to then calculate the peak torque, the continuous torque, and the speed requirements for the application, because those are the three items you need to select a motor. Speaking of level 1, last year we did what we would consider servo level 1 sizing. That webinar is still available, and the URLs are listed here. So please feel free to download those webinars and view them later if you have if any of the topics here are confusing to you. I also want to note that in this webinar there's a lot of calculations. We're not going to spend a lot of time reviewing the calculations. We did put them in a format that should be easy for you to find later and review, but we want to spend more time on the critical topics and discussions rather than going through the calculations. Now, for today's example, we're going to, there's many examples of autonomous robots moving around through warehouses and moving products through warehouses. We're going to focus on a robot that sort of looks like this one. And every time we do a sizing application, we're really looking at, we have to start with what the customer's needs are. And the customer really is the end user. And the customer needs, in this case that we're going to focus on, will be just really three things. One, that the maximum load that the robot needs to carry is 65 kilograms. Two, that the battery voltage is well regulated and always at 168 volts. That may be ideal, but that's what we're going to use. And three, the longest move, which Bob will discuss later, has to be done in about 40 seconds or less than 40 seconds. So those are going to drive us to make a lot of the decisions we're going to make today. And here is our simulated robot, and I'm going to now turn the presentation over to Bob Comstock.
Thank you, Dan. Good afternoon, everyone. Welcome, and thanks for attending our webinar. As Dan mentioned, this is the system we will be analyzing. We have a robotic forklift with a mass of 190 kilograms. That's a weight of about 418 pounds, by the way. And that includes a maximum load of 65 kilograms, or about 143 pounds of weight. The customer has specified a wheel diameter of 6 inches. That gives us a 3-inch radius. And one of the wheels is driven by a traction motor, while the other 3 are free to rotate. The lifting platform, with a mass of 4 kilograms, or about 8.8 pounds, is driven by a ball screw, as Dan mentioned. We will analyze the motion shown here, which illustrates all the sizing concepts. The lift will raise the maximum load 1 foot off the floor. Then the robot will move 100 meters to a delivery point at a speed of about 7 miles an hour. Then the load will be lowered to the floor, and that ends the motion that we're going to discuss. Obviously, in a real environment, the motions are going to be much more complex, but this will really, I think, demonstrate all the key features of sizing that you have to consider in any application. The timing for the system is shown here. The load is lifted to position before the robot begins the 100-meter move. After the robot reaches the end position, the load is lowered to the ground. The time to lift the load is 1.8 seconds. The time to move the load 100 meters is 33 seconds. And the time to lower the load is again 1.8 seconds. We're first going to be finding the requirements for the traction motor and then select the motor meeting these requirements. The timing diagram for the traction drive is repeated above. You should be familiar with the formula for finding the distance traveled because that was a subject in our previous seminar. The acceleration-deceleration rate is the change in velocity divided by the acceleration or deceleration time, or 3.125 meters per second, the speed, divided by 1 second, which gives us an acceleration rate of 3.125 meters per second squared. We will use this value of acceleration when computing the force required to accelerate the robot. This is the traction drive system. We have a motor driving one 6-inch diameter wheel through a 20-to-1 gear reduction. Our motivation for selecting 21 gear ratio will be discussed shortly. Our analysis will begin at the wheel and will work backwards through the gear reducer to the motor. Well, first, what led us to select the 20-to-1 gear reduction? Well, it turns out that the cost and size of servo motors increase with their continuous torque rating. So if you want more continuous torque, you have to buy a bigger motor. That's more expensive and obviously takes up more space and more weight. A larger gear reduction reduces the required torque, but of course it also increases the motor speed and the gearbox speed. Fortunately, brushless servo motors are very well suited to high-speed operation, unlike brush motors that suffer from commutator arcing and accelerated brush wear at high speeds. Looking at a motor's torque speed curve, and we'll be doing that a little bit later, reveals how fast the motor can run before there is a significant loss in torque. In our case, the limitation was the maximum recommended speed of the gearbox, which limited the ratio to 20-to-1. We will first determine the wheel torque required for the three different segments shown, an acceleration segment, a constant speed segment, and finally the deceleration segment. Looking at the acceleration segment, the torque tau W1, and the W, by the way, stands for the wheel. That's the torque being applied to the axis of the wheel. So it's the torque tau W1 required to accelerate the total mass of the robot. The torque tau W2 required to accelerate all four wheels of the robot. In other words, in addition to just accelerating the mass of the robot forward, we also have to accelerate the wheels. They're going to rotate faster and faster as we accelerate. Then we're going to consider tau W3 required to overcome the rolling resistance of the robot's wheels. And finally, tau W4 required to overcome the bearing friction of the robot wheels. Jumping to the constant speed segment, where there is no acceleration, we include, again, tau W3 required to overcome the rolling resistance, and tau W4 required to overcome the bearing friction. Finally, during the deceleration segment, we include tau W1 required to decelerate the total mass of the robot, and tau W2 required to decelerate all four wheels of the robot. Note that during the acceleration, the rolling resistance and bearing friction actually reduce the motor requirements. They help us slow down the robot. However, to be conservative, we assume that they're zeroed in this segment, because otherwise we'd have to pick some minimum number that we were sure they wouldn't be below. And it has very little effect, as it turns out, on selection of the motor, because the peak torque requirement actually occurs during the acceleration segment, and time duration of the deceleration is very small compared to the total cycle, so it has very little effect on the continuous torque. Okay, first, our first rotary to linear conversion is the wheel, as Dan mentioned. It converts torque applied to the axle to a force applied to the mass of the robot. You can see the diagram. From the diagram, we see that torque applied to the wheel's axle generates a force where the wheel makes contact to the floor. You can see as you step on the gas in your car, the torque makes the wheel rotate. The wheel is pushing against the road, and that produces a reaction force transmitted to the load via the axle bearing, and that's just the case we have here with our robot. Remembering that torque equals the radius of the wheel times a force, and we know that just by thinking about a wrench. We know if we apply 1 foot of force 1 foot away from the center point of a wrench, we get 1 foot-pound of torque. We can calculate the relationship between torque applied to the wheel's axle to the force applied to the robot. As we recommended in the earlier seminar, we will be using metric units, and we strongly recommend that you use metric units also. You could look at our earlier seminar to see all the reasons we recommend that. Well, we're going to use metric, so we have to convert 3 inches to meters, and that works out to be 0.0762 meters. We can substitute into our equation for torque and find that the torque in Newton meters is 0.0762 times the force applied to the robot. To find the torque required to accelerate the mass of the robot, tau W1, we must first determine the required force. We're all familiar with the relationship F equals ma, and that's what we'll use to calculate that force. And that works out to be just taking the mass of the robot and the acceleration that we derived before, 3.125 meters per second square, that the force is going to be 593.75 newtons. And now I want to point out that we show the calculation in a worksheet table, with the columns of the table correspond to the equations above the table. Just looking at that top table for a minute, we have our equation F equals ma with the appropriate units. Underneath, you can see force, mass, and acceleration, and it's very easy for you to just go through, use that equation and see how we derive the force in newtons. And it's going to be similar in the second table. From now on, I'm not going to go through the table or the calculations in detail, because I think you can see that's very easy to do, very time-consuming to describe, and it would actually be a good exercise if you want to go back and check our numbers, to just look at the tables and see where we got the numbers. But I think we've made it very clear. The second equation and table use the relationship between torque and force found in the previous slide to calculate the torque, tau W1, required to produce the required force. We have that tau W1 equals 45.24 Newton meters. We now calculate the torque, tau W2, required to accelerate the wheels. We use the relationship torque in Newton meters equals the inertia of the wheels, and it's actually all four wheels in this case, which you have to accelerate all four of them. Inertia in kilogram meter squares times the angular acceleration, d omega dt, in radians per second square. D omega dt is sometimes referred to as alpha. You may be more familiar with that term. So we have the inertia of all four wheels is 0.0148 kilogram meter squared. And again, that was based on the manufacturer's data. The angular acceleration of the wheels, d omega dt, or alpha, is equal to the linear acceleration in meters per second squared divided by the radius. And that's shown in the proof box. I think it's very straightforward. You just have to remember that 1 radian corresponds, an angle of 1 radian corresponds to a distance across the circumference of 1 radius length. So if we're doing 1 radian per second, we're doing a speed of 1 radius length per second. And so if we're doing 1 radian per second, it's a speed of 1 radian per second, and an acceleration, since radius is constant, 1 radian per second squared would be 1 radius length per second squared. But you can just go through that proof box to see that. Using the relationships developed on the previous slide and the known linear acceleration of 3.125 meters per second square, we first calculate the angular acceleration, d omega dt, to be 41.01 radians per second square, and then the torque required to accelerate the wheels, tau W2, to be 0.61 Newton meters. Rolling resistance is the torque required to overcome losses in the tires. As the wheel rotates, the tire deforms as the section in contact with the floor flattens. In pneumatic tires, the rolling resistance increases as the tire pressure decreases, since there is more deformation. We calculated the value of rolling resistance to be 0.88 Newton meters based upon some typical values. Our approach is shown in the appendix. Similarly, we calculated a value for the torque required to overcome bearing friction to be 0.07 Newton meters. And again, the approach is shown in the appendix. Clearly, bearing friction is pretty negligible compared to the other torques. Well, we can now add up the torques for each of the segments to find the total wheel torques. We have, during the acceleration segment, tau W, that's the sum of all the torques, total wheel torque, is 46.81 Newton meters. During the constant speed segment, tau W equals 0.95 Newton meters. And during the deceleration segment, tau W equals 45.85 Newton meters. So we have the torque of the axle of the wheel, but now we must calculate the torque reflected back to the motor, shaft via the gearbox. To calculate tau S, or the torque reflected back to the motor shaft, we first divide the drive wheel torque by the gear reduction. We know that a 20-to-1 gear reduction should reduce the input torque by a factor of 20. However, there is some inefficiency that must be accounted for. So we then divide our result by an efficiency factor. Then we must add in two terms, one being the torque required to accelerate the gearbox itself, and the other a friction torque associated with the gearbox. We have that the gear reduction is 20-to-1, the efficiency is 90%, or 0.9, the gearbox inertia is 2.71 times 10 to the minus fifth kilogram meter squared. The gearbox friction torque is 0.15 Newton meters. And then, obviously, we have to take into account that the motor speed is going to be 20 times the wheel speed. And also the gearbox speed will be 20 times the wheel speed. Calculating the resulting motor shaft torque is shown in the table we have. During the acceleration segment, tau S equals 2.82 Newton meters. That's going to be our peak torque. That's higher than any of the others. During the constant speed segment, the torque is only 0.25. That's just rolling resistance and bearing friction. and during the deceleration segment, 2.57 Newton meters. Now we have to add the torque required to accelerate the motor's inertia. We have to add that to the shaft torques that we've just calculated. So the torque to accelerate the motor is equal to the inertia of the motor times the angular acceleration of the motor, or the omega motor dt. But at this point we don't know what the motor inertia is because we haven't selected a motor. So this often ends up being an iterative process. We're going to select a motor, see what its inertia is, add in the torque required to accelerate the motor's inertia, and see whether we're still within bounds. First thing we have to do is do some calculations on the motor speed and acceleration. So using the formulas shown here, we have that the maximum wheel speed is 41.01 radians per second. Wheel acceleration, since we accelerate in 1 second, is 41.01 radians per second square. The maximum motor speed is 820.2 radians per second. That's done by just multiplying the wheel speed by 20. And 820.2 radians per second works out to be 7,832 RPM, which is a critical number because we have to look at our motor torque speed curve to see just how much torque, both peak and continuous, the motor has at that speed. So we're going to take a look at one motor, the FP0207, made by Infranor. Looking at the torque speed curve, we see that the motor has much higher peak torque capability. It's 7,832 RPM than the 2.82 that we've calculated so far for the shaft torque. So we have a pretty good feel. We can probably add in the torque required to accelerate the motor's inertia, but let's go through the calculations. So now adding the torque required to accelerate the motor's inertia of 1.3 times 10 to the minus fourth, that's provided by the motor manufacturer, by the way, 1.3 times 10 to the minus fourth kilogram meter squared, and we multiply that by 820.2 radians per second square, the motor's acceleration, we arrive at a peak torque requirement of 2.93 Newton meters. Again, we just added that acceleration torque to the torque we previously computed. We normally include a 10% safety factor, and when we do that, we divide what we just calculated, 2.93 by 0.9, to come up with 3.26 Newton meters. That's our peak torque requirement. And we, looking at our torque speed curve, we see that we've still got plenty of margin. So we're in very good shape regarding peak torque with this motor. However, we still have a couple more things to consider. We have to consider the motor's continuous torque rating, or sometimes called the RMS torque. Basically, those are the same things. Torque RMS, tau RMS, determines the temperature rise of the motor over the complete profile. Exceeding a motor's tau RMS rating of a motor for a long period of time runs the risk of burning out the windings. As described in the previous webinar, tau RMS is equal to the following. It's the square root of the sum of each of the individual torques squared, the torque for each segment, the acceleration, the constant speed, and the deceleration, each one squared and multiplied by the duration of that segment, and then divided by the total length of the segment. If you go through that calculation, all shown on this slide, we substitute the torque we have calculated for acceleration and multiply that by 1 second, the constant speed segment lasting 31 seconds, so we multiply that torque by 31 seconds, and the deceleration segment lasting 1 second, we calculate an RMS torque of 0.73 Newton meters. Again, we'll include a 10% safety factor here, and that gives us 0.81 Newton meters. Looking at the torque speed curve for the FP0207, we can see that both our peak and our continuous torque requirements are met. So we're in good shape. We have a motor that can drive the load and handle the continuous torque and handle the peak torque. There's one other thing we're going to check. It's maybe not quite so obvious. We're going to look at the inertia match, or the ratio of the motor inertia to the load inertia. I'm sorry, the load inertia to the motor inertia. So a big load inertia would give us a high inertia match. Let's say it's 20 times the motor inertia. We'd have a inertia match or ratio of 20 to 1. And why do we care about that? Well, the reason is that the robot controller would typically include a positioning loop or positioning servo designed to follow a motion profile similar to the one shown in our timing diagram for the traction drive. Servo performance, usually measured in settling time, how quickly a servo responds to an input and how quickly it settles in when the command, a position command reaches a final position. And also very related, bandwidth, servo bandwidth relates to settling time. High bandwidth relates to fast settling time and vice versa. So servo performance is affected by many factors, one of them being the mechanical stiffness of the system. But the one that we're going to consider here is the inertia match, or the ratio of the load inertia to the motor inertia. I'm going to give you some very rough rules of thumb for this inertia ratio. Probably the fastest servo system that I've ever worked on in my career was used for placing semiconductor chips on printed circuit boards. You can imagine these surface-bound chips, you know how tiny they are, they have to put them on a board with very, very tight tolerances, and these people want to put as many chips on per minute as they possibly can. So they're looking for very high throughput, and that means very fast settling times and very high bandwidths. So in those applications, they're usually looking at a inertia match, or the ratio of the inertial load to the inertia of the motor of 1 to 2 typically. And they achieve settling times of a few milliseconds and velocity loop bandwidths of maybe 100 to 200 hertz, and sometimes even higher. Less demanding applications will allow a slower response time and lower bandwidth, with response time increasing with the inertia match. Now we're looking at a traction drive application, and we're going to show some analysis in a minute that will indicate that we can live with much lower bandwidths. Something as low as maybe 5 to 10 hertz bandwidth, and inertia matches of maybe 30, or possibly even a little bit higher than that. This is a plot of a typical position loop's response for 3 different bandwidths: 5 hertz, 10 hertz, and 20 hertz. First, the red section of the plot is the velocity profile, the commanded velocity profile. That isn't the profile that the servo actually achieves, it's what is commanded by some sort of a motion control, probably a computer inside the robot's control section. You can see that it accelerates at exactly the rate that we want our traction motor to accelerate, at 3.125 meters per second squared. It reaches 3.125 meters per second in 1 second. In this case, it's going to run for just 1 second at 3.125 meters per second. That was just to keep the plot on the page so I can show you all the details here. But that really makes no difference in terms of our final settling times, the things we're really interested in here. And then it will decelerate at the same rate that our traction motor is going to decelerate at, or our robot is going to decelerate at. So it's very similar to our application. Next, the commanded position, which is the curve on the left of the sort of S-shaped curves, that is the input to our position servo, and corresponding exactly to the velocity profile. Again, that would be generated by a computer that would be effectively integrating the velocity profile to generate the position profile, and then it would output that profile to a position loop. And finally, we see emphasize the 3 tracking responses of the servo loop. You can say they don't follow the commanded position exactly, but they follow them pretty closely. And in fact, the 10 hertz and the 20 hertz bandwidth servos look like they're pretty darn close to the commanded position. You can also see that the 5 hertz is a little bit farther away. It's got a bigger tracking error, and what we're really interested in is the area, the settling area, when we reach our final position. we're going to expand that area as shown in the highlighted circle to show in more detail just exactly how the three different loops settle. Again, remember the commanded position reaches final value right after 3 seconds. Ideally, it would like you to be right there at the end of 3 seconds, but the servo isn't going to do that precisely. So we'll expand that in this slide. And you can see that the 10 and 20 hertz loops at the end of 3 seconds, they're actually within about 1/4 of an inch. The 20 hertz is essentially within less than 1/10 of an inch of the final position after at 3 seconds. And the 10 hertz loop is about 1/4 of an inch away. However, the 5 hertz loop is about 1.5 inches away. So if you were moving a pallet, you might not want to raise or lower the pallet right away, but you can see after just 1/10 of a second later, the servo settled out, and now it is within less than 1/2 inch, or just about 1/2 inch of the final position. And if you wait 2/10 of a second after the commanded profile has reached it, you're dead nuts there. You could certainly lower or raise the pallet. So the implication is you could have a pretty low bandwidth. At worst, you might want to wait a couple tenths of a second before raising or lowering the pallet after you've commanded the robot to be in a certain position. That's all we're going to say about inertia matching here, but now we have to calculate the inertia match. Well, the wheel converts the total mass of the robot to an equivalent reflected inertia as seen by the wheel's axle. That may not be totally obvious, but we'll go into some justification, and there's a pretty clear proof in the proof box. But the equivalent inertia at the wheel axis that's caused by the mass of the robot, the total mass of the robot, is given by the inertia J in kilogram meter squared is equal to the mass of the robot in kilograms times the radius of the wheel in meters squared. One way to think about why the mass is converted to an inertia is to think that to accelerate the wheel, we must apply torque to the axle. But for the wheel to accelerate, the load must be accelerated. So for a bigger load, more mass of the robot, it's going to take more torque to accelerate the wheel. Well, considering the relationship or the definition of inertia, J equals torque divided by the angular acceleration, the omega dt or alpha, that makes the mass really look just like an inertia as far as the whatever mechanism is driving the wheel, what that would see. So really a bigger mass as far as the mechanism driving the axle of the wheel just looks like a bigger inertia, and the relationship is given there. And I think the proof is quite straightforward. And we don't have time to cover it here, but I think you can go back and it'll work out very easily. Using that formula, J equals in kilogram meters squared equals mass in kilograms times the radius in meters, in meters squared, we have the inertia reflected back from the robot's mass is 1.10 kilogram meters squared. We have to add the inertia of all 4 wheels, and that's because the mass, the inertia we calculated before, is really just the effect of accelerating linearly the total mass of the robot. It does not include accelerating rotationally the wheel, so we have to add the wheel inertia in, and that gives us a total inertia of 1.11 kilogram meter squared. That's the total inertia reflected back to the gearbox, which is driving the axle of the wheel. So we have one more step. Now, how is that inertia, the 1.11 kilogram meter squared that we just calculated, how is that reflected back through the gearbox to the motor? For a gearbox with an n-to-1 reduction, the inertia reflected to the input of the gearbox from an inertia connected to the output is given by inertia in equals inertia out divided by n squared. So a 20-to-1 gear reduction will give you a 400-to-1 reduction in the reflected inertia. Again, I'm not going to go into the proof in detail. It's straightforward, and it's in the highlighted proof box on that on the slide. So using inertia in, the input of the gearbox to the load inertia divided by the gearbox gear reduction ratio n squared, we have that the inertia reflected back to the input of the gearbox or reflected back to the motor is 27.75 times 10 to the minus 4th kilogram meters squared. Now we have to add the inertia of the gearbox, and we get a total inertia reflected back to the motor of 28.02 times 10 to the minus 4th kilogram meters squared. So that gives us an inertia ratio of 21.6 to 1. So we're nowhere near the 1 to 2 that we require for putting semiconductors on a PC board, but it looks like we're plenty good enough for a traction motor. So we feel that that motor is plenty good for this application. Okay, we've got a motor that we're happy with for the traction drive. Now on to the lift drive. Summarizing, the lift platform and load have a total mass of 69 kilograms. The lift is driven by a ball screw. Selection of the ball screw's pitch of 5 millimeters per rev will be discussed shortly. And the inertia and friction of the selected ball screw is provided by the manufacturer and are shown in the diagram. Repeating the timing diagram for the lift system, we note that the peak lift speed is 10 inches per second, and that the change in speed is accomplished in 0.6 seconds. So our acceleration is going to be the 10 inches per second divided by 0.6. Shown in the slide are the calculations used to derive the peak motor speed of 3,048 RPM, and also the peak ball screw acceleration of 532 radians per second square. Again, the calculations are straightforward, and I don't think you'll have any trouble following the calculations. The key numbers are the motor RPM and the motor's acceleration, and ball screw and motor acceleration, because, again, I should have mentioned the ball screw is directly driven by the motor in this case. There is no gear reduction. So the 532 radians per second square corresponds to the motor acceleration and the ball screw acceleration. Well, we have another form of rotary to linear conversion. The ball screw converts the motor's rotation to linear motion of the platform and load, and the motor's torque to force applied to the platform and load. The relationship between motor torque and force applied to the load by the ball screw is given by torque in Newton meters is equal to the pitch of the lead screw in meters per rev divided by 2 pi. That quantity all multiplied by the force that we apply to the load. In this case, the load is the platform and the load on top of the platform. Deriving this relationship utilizes the energy conservation concept. Power in equals power out, where rotary power in is equal to tau times omega, and linear power out is equal to force times velocity. And that is used at the start of the proof in the highlighted box. I won't go into it in detail, but again, I think it's very straightforward to follow it. We see from the relationship between torque and force that the lower the pitch, the less torque is required to apply a given force. On the other hand, the lower the pitch, the higher the motor and ball screw speed. This sounds a lot like we were talking about with the gear reduction. So why did we pick a pitch of 5 millimeters? 5 millimeters per rev. Well, basically, we wanted a very low pitch because we wanted a big effective gear reduction. In other words, a lot of motor speed for a given movement of the load that gives us a low torque requirement for the motor, so we can use a smaller motor. Again, our brushless motors can go at high speed. In this case, though, the maximum ball screw speed limited the pitch to 5 millimeters per rev. So that was basically the smallest we could use. The speed that we got, a little over 3,000 RPM, is no problem at all for the motor, but it was beginning to be a problem for the ball screw. We now have to look at 3 forces to determine the lift force. We have gravitational force. Anytime we're supporting or raising or lowering the load, there's always gravity pushing down, and our motor is going to have to be pushing up to overcome that. We have to worry about the acceleration, deceleration forces. We're accelerating the load up until we reach the 10 inches per second. and that sometimes we decelerate it, so we consider those forces, and finally friction forces. First, looking at the gravitational force, we use F equals ma, and we calculate the force of gravity for the loaded platform to be 676.89 newtons. Again, we have the mass. We know that if we let the load go, it would accelerate at the gravitational rate, and that gives us what the force is, that the force of gravity is applying to the load. Since the motor will always be holding the load up against this force, we treated the gravitational component of the motor torque to be positive. Now we calculate the acceleration forces during each segment of the lift cycle. Note here that we must be careful of the signs when analyzing the lift system, because in some cases gravity will work with us, in some cases it will be working against us. We first calculate the load acceleration in the top table. We just use acceleration is equal to end speed minus start speed divided by the duration, change in speed over change in time, and the calculations are in the table there. Then in the lower table, we make use of the F equals ma and calculate what the force is for each of the segments in the lift cycle. In the next slide, we do exactly the same thing for the drop cycle. Now we add the gravitational force and the acceleration forces and convert the result into a torque. So in the upper table, we just combine gravity and acceleration. Note the signs, because we had to be careful of signs of when gravity was helping us and when it was hurting us. In the lower table, we use the conversion factor we worked out for the lead screw to calculate the resulting torque. And again, similar calculations are shown for the drop cycle. Now we have to calculate the torque required to accelerate the ball screw for each segment of the lift cycle. We have to calculate the torque required to accelerate the ball screw. On this slide, we do that for the lift cycle. We had previously calculated that the motor and ball screw acceleration was plus or minus 532 radians per second square, and we've added that now to the torques that were computed in the earlier tables. And we do the same thing for the drop cycle. Finally, we have to include ball screw efficiency and friction torques to find the required motor shaft torque for the lift cycle. To be conservative, we didn't include the inefficiency and friction in the drop cycle, since energy is always being taken out of the load, so we can use the values previously calculated for the drop cycle. We see that the peak torque requirement occurs during the lift cycle and is 0.83 Newton meters. Also note that the torque required during the 100-meter traverse, when the load is being held at constant height with no acceleration, is the same as the torque required during the pier segment T2, or 0.75 Newton meters when there is no acceleration. T2 was the constant speed segment in the lift cycle. And so we can just use that value when we're computing the RMS torque. We have to include the torques for all the segments. Summarizing the key numbers, we will use to tentatively select a motor. We have a maximum motor speed of 3,048 RPM, a motor shaft peak torque of 0.83 Newton meters, and a peak motor acceleration of 532 radians per second squared. So again, we're going to select a motor, and later we're going to have to look at the motor acceleration torque, but we're going to consider the Infranor FPO 105 for this application. And we see that it has plenty of peak torque margin at 3048 RPM. But now we have to include the torque required to accelerate the motor. And we have from the manufacturer that the inertia is 4 times 10 to the minus 5th kilogram meter squared. And going through similar calculations as we did for the traction motor, we get that the motor torque, tau m, required for each segment of the lift cycle Note that 0.85 Newton meters during the acceleration segment represents the peak or highest motor torque. And doing a similar thing for the drop cycle. We don't have any torques that are as high as the acceleration cycle, but we will have to include those when we work out the continuous or RMS torque. So we have included all the torques, but now we want to include our 10% safety factor, and that gives us a peak torque requirement, again, during the acceleration portion of the lift cycle of 0.94 Newton meters. Looking at the torque speed curve, we can see that we're well within range of the peak torque. The peak torque capability of the motor, that's the blue curve, so we're way below that. No problem with the peak torque. But we still have to calculate the RMS torque, and we do that in exactly the same manner we did in the case of the traction motor, and get a tau RMS is equal to 0.74 Newton meters. But we have to include our 10% safety factor, so we again divide by 0.9 to get 0.82 Newton meters. Looking at the torque speed curve, we can see that we're not way below the continuous torque, but we've included our 10% safety factor, and we are below the continuous torque rating. So we feel we're okay, because again, we put in our 10% safety factor. And again, we haven't made use of the fact that friction and inefficiencies actually reduce the motor torque during the when we're lowering the load. One thing that we should consider is that if you have a very long period, or a very long segment, I should say, like the constant speed segment, during that entire segment, the lift motor is having to support the load. And that requires a fairly high torque. If you have a long segment like that, something like 33 seconds, if you were way above the continuous torque for that period, you could burn out the motor windings. Fortunately, in our case, it works out that even with a 10% safety factor, we're just below the continuous torque. And since it's holding the load stationary, we can look at the continuous torque rating at zero speed, which is always higher than the continuous torque rating at higher speed, as you can see from the torque speed curve. So we're still okay. Sometimes, in some applications, if you had a long segment with a torque that was significantly higher than the continuous torque rating, you could have a problem. So we're satisfied that this motor satisfies our peak and continuous torque requirements. The one last thing that we have to calculate is the inertia match. Again, just thinking about servo performance. Well, the mass driven by the ball screw is converted to an equivalent reflected inertia at the input to the screw, and it's given by the reflected inertia. It was the inertia that the motor driving the screw sees is equal to the pitch of the ball screw divided by 2 pi, all squared, times the load in kilograms. And that's the pitch in meters per rev. The proof makes use of the definition of inertia. That the inertia in kilogram meter squared is equal to the torque divided by torque in Newton meters divided by the angular acceleration d omega dt in radians per second. Radians per second squared, I'm sorry. And it's presented in the shaded box. Again, it's relatively straightforward to follow. And in the interest of time, we won't go through it. But using this relationship and substituting our load and pitch, we find that the load is, the J reflected back to the motor, or J load, is equal to 4.37 times 10 to the minus fifth. But we have to add the inertia of the lead screw, and that gives us the total inertia reflected back to the motor of 1.44 times 10 to the minus fourth. So the inertia of the motor that we've selected, the FPO 105, is 4 times 10 to the minus fifth. So we can now calculate the inertia match, which works out to be 3.6 to 1, ratio of the load inertia to the motor inertia. So that's good. We could have a really fast selling time on our our lift motor, even though we probably don't need one, but our real consideration was the meeting the peak and continuous torque requirements. So congratulations, you have now successfully selected motors suitable for the traction drive and the lift drive. Now Jack Curl will discuss the selection of drives suitable for the motors.
Thanks, Bob. Pardon me. Hello everyone, this is Jack Curl, and I'll be reviewing the drive selection process. To select the appropriate drive power level, you only need to determine the voltage available, the peak current required, and the continuous current required. The voltage required is determined by the customer. In this example, we have 168 volt DC available coming from a battery supply. The current required is determined by the motor's torque sensitivity, also known as KT. KT is defined as the amount of torque the motor can produce per amp of current and is based on the windings selected during the motor selection process. Please note, the motor inductance, drive bus voltage, and drive PWM frequency determine how much PWM current ripple you will see in the motor. The drive has a minimum value allowed for stable operation. Check the drive specifications for this value. If the motor inductance is too low for the drive, you can change the drive PWM frequency. You'll have to derate the drive to do that, or add external inductors to the motor leads to reduce the ripple current. Since current in amps RMS is equal to torque in Newton meters divided by the motor's KT in Newton meters per amps RMS, and since the traction motor KT is 0.16 Newton meters per amp RMS, then we need a peak rated current of 2.93 divided by 0.16 or 18.3 amps RMS. And we need a continuous current of 0.81 divided by 0.16 or 5.1 amps RMS. So we need a drive that can supply at least 18.3 amps peak and 5.1 amps continuous. We chose a pack AK400/20 to do the job with 20 amps peak and 10 amps continuous. The motor inductance is 0.2 millihenry and is below the drive specification for standard PWM frequency as minimum inductance. To accommodate for the low inductance, we needed to increase the PWM frequency and reduce the drive rated continuous current. So 10 amps RMS is reduced to 7 amps RMS continuous, and even with this derating, there's plenty of current available. Looking at the torque speed curve, the red and violet dotted lines represent the motor and drive system limits. Notice we could select a higher power drive to get more power out of this same motor, although that would increase the drive weight, size, and cost. Using the same process for the lift drive, this time the KT is 0.29 Newton meters per amp RMS. So the required current is 3.24 amps RMS peak and 2.86 amps RMS continuous. So we need a drive that can supply at least 3.24 amps peak and 2.86 amps continuous. We chose a pack AK400-08 drive to handle this requirement. It can supply 8 amps RMS peak and 4 amps RMS continuous. This drive can handle 1.3 millihenry at the normal PWM frequency, so no derating is required. Note there are other criteria to selecting a drive, such as field bus compatibility, STO requirements, feedback options, and more. You can contact the manufacturer for assistance. For more details on selecting a drive, please see the appendix on drive selection. Thank you for attending, and please stay online for Q&A.
All right. A few of you have already submitted questions, so we're going to jump right in. While our presenters are answering your questions, please take a moment to answer the feedback form that will appear on your screen. If you have pop-up blocker, we ask that you disable it so that you can receive that form. So, first question. the thermistor properly connected should protect the motor, correct? But the position loop will go open loop.
So that's a question about the motor PTC or NTC, whichever is used in the motor. This is Jack Curl. I can take that question. The PTC has a sensor in it to measure the temperature of the motor, and so if the current of the motor is above the motor's current rating for a certain amount of time, the motor will heat up, and the PTC is used to protect against the motor overheating. But the motor winding has a fairly long thermal time constant, and if you are excessively putting in current into the motor for a longer period of time, the PTC may not react to that quick enough to protect the motor. So most drives have an I2T functionality in them built in to protect the motor in that situation.
Where there's a lot of peak current.
Where there's a lot of peak current for a long period of time.
Okay. And what if the traction gear reduction was done with belts instead of a gearbox?
Okay, this is Bob Comstock. I'll talk about that. One of the things I mentioned in terms of servo performance was that to get good performance, the stiffer the system, the better. And clearly belts are not terribly stiff. They're very inexpensive. It's a great way of getting gear reduction. But you might get away in a traction drive with belts. It's something you'd really have to analyze. But belts in servo systems are a major source of problem. Number one, they're not stiff. So you get relatively low-speed resonance where sometimes the belt oscillates in different modes, and that can cause servo systems to go very unstable. So you have to be careful with belts.
Okay. And how long can it run? How much time can you spend at peak torque?
Yeah, that's a good question. It's a complicated question in that let's say that you were running at continuous torque for a long period of time where your motor is already pretty hot. It's within range, but it's pretty hot. Now if you put peak in, the winding is going to heat up quite quickly. And since they're already probably pretty close to their limit, you wouldn't want to be there very long at all. The general rule of thumb is you don't want to run at peak for more than a few seconds. But again, that would depend. If the motor was stone cold, you were really had an easy application except for a few moments of peak. You might be able to get by with several seconds at peak. But if it's already hot, you probably don't want to be at peak for more than a second.
Okay. When you move the load down vertically, do you worry about regeneration?
Okay. Yeah, we can answer that. This is Jack Curl. Normally, you would consider regeneration for higher speed applications, like the one we have is 8,000 RPM for the traction drive. And you would consider the regeneration because the energy that's put back into the motor is based on the inertia and the square of the speed. And so the higher speed applications make more energy by the square of the ratio of the speed. And so you would worry about that in a normal application, that the energy going into the motor would have to go back into the drive as well, and that energy would pump up the bus voltage until you get an over voltage fault in the drive, unless you have a regen resistor system in the drive. And sizing the regen resistor is something the factory can help you do based on the energy that's calculated into the system. In our application that we sized, it was a battery application, and all of the energy is going to be dumped into the battery, which means it's just going to recharge the battery and be stored there for later use.
Like a Prius.
Yeah, like your Prius.
Uh-huh. And I think we can squeeze in one more question here. How do you determine the drive derating percentage?
Okay, this is Jack Curl again. I believe that's related to changing the PWM frequency to the higher PWM frequency. And that is determined by the drive design team. So the drive manufacturer will allow you sometimes to change the PWM frequency on the drive. And if you double the PWM frequency, typically you have to reduce the rated current by 30%. But if you have other increments of increasing the PWM frequency, you have to contact the manufacturer to determine how to derate the drive.
All right, very well. Well, I'm afraid that we've run out of time. On behalf of the Pensions Design Engineering and Sourcing Group, I'd like to thank you for joining the webcast today. Thank you to Infranor for sponsoring this event for us today. Have a productive remainder of the day.
Thank you.
Thank you.